the session. And today we have our very first speaker from KAIST, Dr. Yuyol Shin. Dr. Shin is a postdoctoral researcher in Department of Civil and Environmental Engineering, and he will share his research on the short-term traffic forecasting in urban areas, element-wise performance evaluation in diverse city study sites. Please welcome. 참여해 주신 안녕하세요.
안녕하세요.
시간 내주셔서 감사합니다.
Okay, so good morning, everyone. First of all, it is really an honor to present my research to all of you on this Urbanics seminar. I'm currently working with Yoon-jin as a postdoctoral researcher at the lab, and these studies have been conducted under supervision. And as Yoon-jin introduced, this is the title of my talk today, and let me get started. This is the contents of the presentation. First, I will introduce performance evaluation of building block of deep learning models for traffic forecasting, then explain the approaches to improve the performance of traffic forecasting studies. In the field of transportation engineering, traffic forecasting has been a field that garnered research interest as a key technical enabler of adaptive traffic management. It is a problem to predict the future traffic state based on historical traffic states. It has increasingly gathered research interest over past 10 years, as you can see in the right figure. When the keyword traffic forecasting is searched on the Web of Science, the number of publications has increased nearly by 2.5 times over the past 10 years. Accurate traffic forecasting can actually help develop user-friendly applications such as navigation system, congestion prediction, adaptive signal control, and for last but not least, carbon emission estimation. And spatial temporal extraction method for traffic forecasting methods can be grouped in 2 and 3 categories. For temporal, there are RNN, gated convolution, self-attention, and for spatial dimension, there are convolutional GNN and attentional GNN. There are many studies being proposed, but there's no specific reasoning for choice of each category or each building blocks for these models. And there is need to investigate the differences among the groups of methods. When we searched 46 traffic forecasting studies by building block categories, it is grouped as in the right table, but there is not specific leading model among this field of traffic forecasting studies. And if you add up the numbers in the table, it does not add up to 46 studies, since several models use more than 2 blocks to model extract temporal features or spatial features. The research goal of our study is to identify the differences among the building blocks of spatial temporal traffic forecasting models. And our objective is set as to conduct extensive experiments using spatial and temporal feature extraction methods, which are RNN, convolution, and self-attention for temporal feature extraction, and GCN and GAT for spatial feature extraction. And we made a multifaceted performance evaluation on building blocks of traffic forecasting models on 4 different real-world data sets. And we identified the trends of forecasting results of each basic building blocks. And there are some preliminaries of our study. We defined transportation network graph as directed graph, and the traffic data generated from each node of the graph is defined as node signals, and aggregating all the node signals of the graph, it is called graph signals. The traffic forecasting problem is to predict all traffic states for the next p time steps using traffic states of h historical time steps. And this is the overall framework of this comparative study or performance evaluation study. Using basic building blocks of traffic forecasting models, we conducted extensive experiments and compared the results. Also, we used 4 different real-world data sets with different characteristics to identify the tendency of each method in different study areas. These data sets all have distinguishable structure and environmental characteristics, such as one has highway speed data and the others have the urban speed data. Others have urban speed data, while the last one has the highway flow data. This illustration shows the difference between the 2 spatial feature extraction methods, which are convolutional GNNs and attentional GNNs. The basic idea of these 2 GNNs are the same, where both GNNs aggregate the information from neighboring nodes. The difference lies in how they aggregate the information from the neighbor nodes. The convolutional GNS directly learns the scalar parameter to control the information, while attentional GNS controls information by using a function of source and target node features. For temporal feature extraction, we implemented a model representing each of RNN, convolution, and self-attention from previous studies, namely TGCN, GraphWaveNet, and GMAN. We replaced the spatial feature extraction modules in those models with GCN and GAT to make a comparison between basic building blocks. For datasets, we used 4 real-world datasets with all different characteristics. The first is PAMS-Bay. This is a popular traffic dataset which contains highway speed in Bay Area. And the second one is Meta LA, which contains highway traffic flow, and the others are urban data sets. The first one is Urban Core, which contains urban speed, and the other is Urban Mix, which has a mixture environment with both highways and urban road segments. The data sets differ in the duration and the number of nodes, and they have all same frequencies of 5 minutes. The left table here shows the summary of data sets. In terms of spatial scale, Urban Mix is the largest with 1,007 nodes. And for duration, PAMS-Bay collects the most samples, and we evaluate the complexities of the data sets using approximate entropy, as in the right figure. As it is shown, the complexity becomes higher for flow data set than the speed data set, and it becomes higher for urban data sets than compared to highway data sets. The right figure shows the sample, the approximate entropy is in the last row of the table, and the right figure shows the samples of data.
이 Urban X 여기 이 세미나 트래픽이고
Is the result on PAMS-Bay and
굉장히 가까운 거는 한수령
Meta LA.
전화하니까
GraphWaveNet with convolutional GNN generally shows the best performance, while GMAN GAT shows more competitiveness in 60-minute predictions. These are the results on urban data sets. As you could see in the previous page, similar results has been shown in the highway data sets and the urban data sets. An interesting characteristic of GMAN is that the performance difference does not change very much for 15-minute prediction and 60-minute prediction. This somewhat aligns with the current study trend that long-term traffic forecasting models usually use transformer-based models, while the short-term traffic forecasting models use both convolution and self-attention models. And this shows the performance of the models in different traffic categories. In PAMS-Bay, as in the left table, GraphWaveNet demonstrates the best performances in the most frequent categories, such as 60 to 65 and 65 to 70 miles per hour categories. While the attention model shows a competitiveness in rather infrequent categories, such as 0 to 50 miles per hour category. In other data sets, similar results has been observed. Against the outliers, the self-attention models show more robustness than RNN and convolution. As you could see in the red circled area, this GraphWaveNet and RNNs show delayed reaction to the outliers, showing like large drops after the outlier has been observed. And also in attentional GNNs, they show more robust results compared to the convolutional GNNs, as in the right figure. The conclusion of our study is that we categorized the building blocks for spatial temporal deep neural networks for traffic forecasting. The first, in the temporal feature extraction dimension, there are 3 building blocks, which are RNN, convolution, and self-attention. On the spatial dimension, there were convolutional GNN and attentional GNN. Also, there are some miscellaneous categories, but those are not the major approaches in these studies. So we categorized the building blocks into these 5 categories. And we conducted an extensive multifaceted experiment using 6 forecasting models on 4 different data sets. The overall performance evaluation discovers building block pairs that generally yields higher accuracy, which was convolutional GNN and convolution, and attentional GNN combined with self-attention. Convolution models maximize the performance gain in more frequent traffic categories, while self-attentions and attentional GNNs showed increased robustness in rather infrequent traffic conditions, such as low-frequency traffic categories, traffic transitions, and against the outliers. Based on this finding, we suggested 2 approaches to improve the performance of traffic forecasting performance. The first one is adaptive model evaluation framework, and the second was to enhance the model with convolutional GNN and convolution. The first one is adaptive model evaluation framework for each framework. For each traffic category, it first checks which model performs actually better on a validation set. Then with the selected model, the performance evaluation is made with on the test set. And with this simple framework, it shows ability to improve the performance of the traffic forecasting in all study sites. The performance gain has been larger in Thames Bay and urban mix, while in Metro LA and in urban core, some metrics has been in some tasks, adaptive evaluation does not bring advantages. The next one is the enhancing the model with convolutional GNN and convolution. In this study, we proposed the methods to how to better aggregate the information of neighboring nodes by defining which are the neighbors of target nodes. The spatial correlation between different regions can actually vary with time, and such change is tightly coupled with real-time online traffic data. However, in current studies, in most current studies, only the structural information or structural connectivity of road transportation network is considered. So in this study, we tried to incorporate the time-varying dynamic spatial correlation of the transport traffic data. For example, the school and offices may have similar traffic patterns in the morning, which leads to high correlation between those 2 areas. But in the afternoon, the peak times is different for those 2 places, and this leads to low correlation in the evening commute time. To model such a spatial correlation from online traffic data, we suggest the progressive graphs to represent dynamic spatial correlation. It utilizes cosine similarity between node signals with learnable parameters to extract the dynamic edges. As in the right figure, the progressive graph constructor takes online traffic data and constructs a graph at each time step. This is the entire architecture of the PGCN. It consists of multiple spatial temporal layers, and in each spatial temporal layer, we first extract temporal features with temporal convolution. Then we extract spatial features through graph convolution with both progressive and structural graphs. Residual and skip connections are set in between and within layers to have the final prediction outcome. And this is the performance of PGCN in 6 different datasets. In the results, we could find that PGCN achieves the state-of-the-art performance in all datasets and prediction horizons. For MAE, the PGCN is ranked the first among the baseline models unless it takes the runner-up place, but only by a small margin. So for the conclusion, we proposed an adaptive evaluation framework for traffic forecasting, which makes predictions using multiple models based on the performance of distinct traffic categories. The framework increases the previous state-of-the-art performance by 3.7% in a highway traffic speed prediction test. And the point is that we did not further sophisticate the models by changing the architecture of the models. And the second approach was, the name of the model was Progressive Graph Convolutional Network, and it has been proposed to reflect dynamic time-varying spatial correlation of online traffic data using convolutional GNNs and temporal convolutions. And the results of PGCN shows ability to consistently yield the state-of-the-art level performances in all datasets. Thank you for your attention, and this was it for my presentation.
Thank you very much, Dr. Shin. We have a question from Seyun that if you have any, sorry. Yeah, we and Dr. Shin has been working with me, so I and some of the participants here from our research lab understand this study so well. So we don't have a specific question for you. Maybe I can ask this question though. Well, about this study, people, the usual question that I get a lot is that how we can use this knowledge to the real world problem, like estimate time of arrival and congestion management and things like that. So do you have any intuition about that?
So for the applications in the real world situations, there are several examples. So with the accurate traffic forecasting, we can have better navigation system, since it, of course, contains the information about the ETA, estimated time of arrival, and actually by getting how much traffic flow or what is the traffic speed of the future, we can also predict the congested areas of urban area or the transportation network, and it may be in more future, but adaptive signal control is also possible using traffic forecasting. I mean, traffic forecasting is a crucial component of adaptive signal control, and through also, it enables the carbon emission estimation of transportation network, since the carbon emissions are usually calculated with the traffic speed or acceleration and how much cars are there.
Can I ask a question about, so you're looking at a very fine-grained map of a city, and presumably nowadays there's also information about how large building structures are, and like how high, how tall the buildings are, and you could also estimate how many people might be residing in each building, or even the types of the area. Is it residential, or is it, you know, in business area, whichever, or the parks. And also you mentioned the carbon emission, and you could also start counting trees, how many trees are there. So could your findings also say something about like how we place large structures and how that's going to shape the buildings if you look at the before and after patterns? So design of a city architecture, and like, you know, like setting, like, you know, if you put large structures like 신세계, and then we definitely see the traffic starting to change. So if you look at the temporal patterns over time, I don't know if this is only 1 month data, but even within that 1 month, I assume there would have been some changes in the city.
Yeah. That's a really interesting approach in this. It's not exactly the same, but in like other studies, there are efforts to incorporate those like already existing information. So like what is called point of interest. So if there are so those studies try to model the impact of such structures as department stores or other like the land usage into the like forecasting of the traffic states. But yeah, I haven't thought of like that would be something that is like the different direction of the thinking, and I look more into that.
Let me add the one comment to the in addition to Professor Cha's. Well, first of all, it's very interesting. Similar ideas actually grow up in the same school, because you know we thought about this approach, and the well, especially the traffic, the differences depending on how people depending on people's behavior. So in the morning time, more, you know, traffic, and then during daytime, especially school. So depending on the what purpose of the human flow, we call this human flow, the traffic may be getting influenced. So quite similar the thinking, but we try to add the human movement on the road. So we try to extend the convolution network, the graph neural network, not only just kind of physically connected one, but also the semantically connected. So from the home to workplace. So the first glance, the road may not be directly connected, but semantically they are connected, because a lot of people actually moving from their home to workplace. So they are connected to. So when we actually added that, we got pretty good performance. So if you are interested, our paper is going to be presented next 2 weeks in CKIM. So contact our student, or I'll just kind of give you the URL. So if combine your idea and so on, but so I think we are looking at the same direction. But what I'm trying to say is not only just because, you know, you're the approach to incorporate depending on the time, traffic may change. So looking, not just kind of treating the signal data in syntactical way, but also semantic way, I think that gives a lot of the new improvement that we can get. So it's just a good approach. Thank you.
Yes. So maybe just adding on to like the the imagination that I had while listening to your talk was, we have new cities like Sejong시, which is entirely new. From the scratch, we can have a design, and the cities keep remodeling. We have the old part of Daejeon that's being reconstructed, and also Jakarta moved to the capital of Indonesia has moved to an entirely new city because of sea level rises, and a lot of cities will start moving to new locations. So a lot of governments will have to completely design from scratch. And if we have, Ujucheong, it's going to be entirely new city as well. So I think there's we'll continue to start building entirely new places, and we don't want to have congested road and something really centered around small areas like Gangnam. It's a horrible design. So if you can give some design insights, or maybe change that to a park, and how would that change? So if you have implications, I think globally there's a lot of momentum to really design cities, redesign, or entirely build something new. So it could be pretty impactful.
Yeah, I just said about, as Dr. Kim said, the POI incorporated the graph convolution network transformer already. They studied it several years, but the POI itself only just kind of the one spot, so one dimension. As Dr. Kim said, but even same POI, depending on the time, depending on what kind of people actually visit such POIs, very different. So how we can incorporate such what could I say, the visitors flow, if we can incorporate the meaning of the visitors flow, traffic estimation can be more improved. And also, I think the urban form changes, we can predict much better performance with a much better performance.
Yeah.
So if you try to, I think that you better try to incorporate not only just the synthetical data, but also the meaning of the changes. Then we can get better performance.
Right, I'm just writing down your comments here. So I get, thank you so much for the new ideas. I guess we can sort of summarize this, your the comments in three different directions, which is the first one is sort of the intervention study that how it's gonna interact with the built environment when there is a significant change in the built environment. That can be one direction that we can take. And I've been kind of shooting the moon with the kind of similar idea, but didn't really sound like it first, by incorporating the intervention from the autonomous vehicle. That when we have sort of mixed environment in terms of the vehicle capability, maybe this type of study can shed some light on how or what type, what level of speed that each autonomous vehicle should have to drive safely in the mixed environment. So the intervention study is something that we have been kind of brainstorming a lot. And in a built environment, we never actually thought about it, but it's a really interesting idea. For the incorporating or the utilizing another auxiliary information about the urban semantics based on the people movement, I have another postdoc who used to work kind of in the similar context using heterogeneous graph attention network. So we also utilized the people's OD movement, how the frequency and the POI, and how often people checked in at a Starbucks or something like that. So there is a branch that we have been developing quite a lot. So I think we can make a sort of the immediate connection there. So for the intervention and the urban semantic study, we're definitely interested in working with other teams. I mean, Dr. Shin has graduated, so he's been spending some time working with Finnish researchers for maritime artificial intelligence for the Green Corridor project in Finland, and we are in the process of expanding the study with the people in the research in the U.S. so that we can have a sort of multi-region study. So this GCN and the GAT in terms of the traffic application has a lot of potential to for the paper and then to actually develop the tangible sort of the green technology. So I look forward to to the follow-up conversation with both of you. And we have another question from Seyun. Some people might think the current performance of the traffic forecasting is accurate enough for real life situations. Do you think we need to research to improve accuracy or develop methods to forecast in special situations? So I guess, yeah, so you go ahead.
Yeah, that's a really good question. So as Seyun mentioned, the performance of these traffic forecasting models has been somewhat saturated in current studies. And while there are several papers still being published on the improving overall performance of the traffic forecasting models, there are more increasing efforts on developing methods to for the latter one, methods to forecast in spatial situations, such as where the sensors are malfunctioning. So where there are missing data, how would the model predict the those states for those times, or transfer learning is another approach that is usually used. And the types of approaches are really frequently used, and yeah, that's current research trend, and I think that direction is also makes sense to me. So I hope that answers to your question. Thank you.
All right. I guess that wraps up our Q&A session. I'd like to thank everybody for coming again. Next week, we have Joseph Chow from NYU. He's going to talk about kind of similar, but a little different, transportation study. Joe is a kind of rising star at NYU in transportation. So I'm really looking forward to this talk. So please come back again. Yeah, I'd like to see everyone back again in next week. All right. Okay. So I guess we can wrap up here. Okay, thank you, everybody.
Thank you.
Thank you, Dr. Shin. 부총장님, 참여해주셔서 감사합니다. 감사합니다.
네, 잘 들었습니다. 네, 감사합니다.